Right now, physicists have measured something that should not exist. In laboratories across the world, particles are behaving as if they occupy multiple states simultaneously until the moment we observe them. This is not equipment malfunction. This is quantum mechanics operating exactly as the equations predict. The problem is what those equations actually say. They describe a reality where every quantum event splits existence into parallel branches, where every choice you make creates a universe where you chose differently, where infinite copies of you are living every possible version of your life right now. 3 independent branches of physics, quantum mechanics, cosmology, and string theory have converged on the same impossible conclusion. Our universe is not alone. We exist in one reality among infinitely many. The mathematics demands it, the observations support it, and if it is true, everything you think you know about existence is wrong. We will examine the quantum measurement problem that forces parallel worlds into existence, explore how cosmic inflation creates infinite bubble universes, and confront the evidence that we have already detected other realities. If you are ready to question the singularity of existence, hit that like button and subscribe. Prepare yourselves, we begin. 3 physicists fired electrons at a metal plate with 2 slits cut into it, one at a time, single electrons. Behind the plate sat a detector screen that would record where each electron landed. The expectation was simple. Each electron would pass through one slit or the other and hit the screen directly behind whichever slit it chose. After firing many electrons, 2 bright bands should appear on the screen, one behind each slit. That is what particles do. They go through one opening or the other. The electrons did not cooperate. Instead of 2 bands, an interference pattern emerged. Multiple alternating stripes of light and dark across the screen. This pattern is the signature of waves, not particles. Waves passing through both slits simultaneously, interfering with themselves, creating regions where they amplify and regions where they cancel out. But these were electrons. Individual particles fired one at a time. There was no wave. There was one electron. The result makes no physical sense until you accept what the mathematics has been screaming since 1926. The electron does not choose a slit. It passes through both, simultaneously. Not as a particle, but as a wave function, a mathematical description of all possible locations the electron could occupy. The wave function travels through both slits, interferes with itself, and only when it hits the detector does it collapse into a single point. One electron, one impact. But the pattern that builds up over thousands of electrons reveals that each one somehow knew about both slits. This is the double-slit experiment. It has been performed thousands of times with electrons, photons, atoms, even molecules. The result never changes. Quantum objects exist in multiple states simultaneously until observed. Then something happens. The wave function collapses. All possibilities vanish except one. Reality crystallizes at the moment of measurement. But here is the problem that has tortured physicists for nearly a century. What counts as observation? What causes collapse? When you place a detector at one of the slits to see which path the electron takes, the interference pattern vanishes. The electron behaves like a particle again, going through one slit only. The act of measurement changes the outcome. Not because we disturb the electron physically. The detector can be passive, absorbing nothing, merely recording information. The electron still behaves differently. Consciousness does not cause collapse, despite what popular science suggests. An automated detector with no conscious observer produces the same effect. But something about gaining information about the system forces it to choose. The universe will not let you know which slit the electron used, and also see the interference pattern. You can have one or the other, never both. This is complementarity. It is not a limitation of our equipment. It is a feature of reality. The mathematics of quantum mechanics describes this precisely. Schrödinger's equation governs how wave functions evolve over time. It is deterministic. Given the wave function at one moment, you can calculate it at any future moment with perfect accuracy. But the equation describes a wave function that contains all possible outcomes simultaneously. An electron that is here and there and everywhere it could be, all at once, weighted by probability. When we measure, the wave function collapses. This collapse is not part of Schrödinger's equation. It is an additional rule, inserted by hand, called the measurement postulate. Without it, the math describes a universe where particles never have definite positions, where everything remains in superposition forever. But we observe definite outcomes. Electrons hit specific points on the screen. Cats are alive or dead, not both. Reality appears classical at human scales. Therefore, physicists added collapse as an axiom. When a measurement occurs, the wave function randomly selects one outcome from the probability distribution and discards all others. This works. It predicts experimental results with absurd precision. Quantum mechanics is the most accurate theory in the history of science, but it requires two contradictory rules: smooth deterministic evolution described by Schrödinger's equation, and sudden random collapse described by the measurement postulate. This is the measurement problem. It has no agreed solution. The standard interpretation, called the Copenhagen interpretation, simply accepts both rules without explanation. It treats wave function collapse as fundamental, something that just happens when measurements occur. Do not ask what a measurement is. Do not ask what the wave function represents physically. Shut up and calculate. The equations work. That is enough. Except it is not enough. Because the measurement problem hides a deeper crisis. If Schrödinger's equation is fundamental, collapse cannot be. If collapse is fundamental, Schrödinger's equation is incomplete. Physics requires one consistent set of laws. We have two incompatible rules depending on whether we are measuring or not. Hugh Everett proposed a solution in 1957. His doctoral thesis suggested something radical. What if collapse never happens? What if Schrödinger's equation is the only rule and it always applies without exception? The wave function never collapses. It continues evolving, describing all possible outcomes simultaneously. When an electron reaches the detector screen, the universe does not choose which point it hits. Instead, the universe splits. One branch where the electron hit here, another branch where it hit there. Every possible outcome occurs in a separate, equally real branch of reality. This is the many worlds interpretation. It eliminates the measurement problem by eliminating collapse. There is no magic moment where possibilities become actualities. All possibilities remain actual in separate branches. You, the observer, also split. One copy of you sees the electron hit one location, another copy sees it hit elsewhere. Both versions of you are real, existing in parallel branches of the wave function. You simply cannot communicate with your other selves because the branches decohere, becoming isolated from each other. The theory sounds insane. It multiplies universes recklessly. Every quantum event splits reality into countless branches. The number of parallel worlds grows exponentially with every passing moment, trillions upon trillions of universes spawning every second. But Everett's interpretation has a shocking feature that makes it impossible to dismiss. It requires no new physics. It is simply quantum mechanics taken literally. The equations already describe all outcomes occurring simultaneously. Many worlds just refuses to add an artificial collapse mechanism. Standard quantum mechanics says the wave function is not real, just a mathematical tool for calculating probabilities. Many worlds says the wave function is reality itself. Everything the wave function describes actually happens. You do not live in one universe where quantum events have definite outcomes. You live in a constantly branching multiverse where all outcomes occur. The interpretation was largely ignored for decades. It seemed too extravagant, too philosophically disturbing. But it gained traction as physicists confronted the measurement problem more seriously. If you take quantum mechanics at face value, if you believe Schrödinger's equation is truly fundamental, many worlds is the logical conclusion. No collapse, no special role for observers, no division between quantum and classical regimes. Just one equation describing everything, and that equation produces infinite parallel realities. Modern formulations of many worlds focus on decoherence, the process by which quantum superpositions become effectively classical. When a quantum system interacts with its environment, the different branches of the wave function become entangled with vast numbers of environmental particles. This entanglement spreads the superposition across so many degrees of freedom that interference between branches becomes impossible to detect. The branches decohere. They still exist within the universal wave function, but they evolve independently, unable to affect each other. Decoherence explains why we do not see macroscopic superpositions. A cat cannot be both alive and dead from our perspective, because the cat's quantum state immediately decoheres through interaction with air molecules, photons and thermal radiation. Within a fraction of a second, the alive branch and the dead branch separate into isolated worlds. You find yourself in one branch or the other. The other branch still exists, containing another version of you who observed the opposite outcome, but you cannot access it. This makes many worlds testable in principle. If decoherence can be prevented or reversed, quantum superpositions should persist at larger scales. Experiments with superconducting circuits and trapped ions have created superpositions of increasingly large systems. The current record involves objects containing billions of atoms in superposition. These experiments confirm that quantum mechanics applies without modification at larger scales when decoherence is suppressed. The wave function does not spontaneously collapse just because something gets big. It only appears to collapse when information leaks into the environment. Therefore, the evidence suggests Everett was right. There is no collapse. There is only branching. Every quantum measurement you make creates a version of you in each possible outcome branch. Those versions are as real as you are. They are you. They just exist in parallel branches of the universal wave function, forever isolated by decoherence. Right now, as you read this, quantum events in your brain are causing it to split. Neurons firing or not firing based on quantum fluctuations. Each fluctuation creates branches. Some versions of you will finish this sentence, others will look away. All of them are real. All of them are happening. The multiverse is not a distant abstraction. It is being created inside your skull every millisecond. The equation that governs reality is shorter than a tweet. It contains no constants, no approximations, no arbitrary assumptions. Schrödinger's equation describes how every quantum system evolves through time with absolute precision. And when you solve it honestly, without inserting artificial collapse mechanisms, it produces infinite universes whether you want them or not. The equation operates on the wave function, typically written as psi. This mathematical object contains everything knowable about a quantum system. For a single electron, the wave function assigns a complex number to every point in space. The square of that number gives the probability of finding the electron at that location if you measure it. But the wave function itself describes something stranger than probability. It describes the electron existing everywhere simultaneously with different amplitudes. When Schrödinger first wrote his equation in 1926, physicists treated the wave function as a convenient fiction, a calculational tool, nothing more. Max Born proposed that only the probabilities derived from the wave function had physical meaning. The wave function itself remained abstract. This interpretation became standard because it avoided uncomfortable questions about what the electron was doing between measurements. But mathematics does not care about comfort. The wave function obeys a precise differential equation that determines its evolution through time. Given psi at time 0, you can calculate psi at any future time by applying Schrödinger's equation. The evolution is smooth, continuous and deterministic. No randomness, no ambiguity. The wave function flows through configuration space like a fluid following fixed dynamical laws. Here is what that evolution actually describes. Take a quantum system in a superposition of two states, an electron that could be spin up or spin down. The wave function is a sum of both possibilities, each weighted by an amplitude. When the electron interacts with a measuring device, the combined wave function of electron plus device evolves according to Schrödinger's equation. The result is a superposition of two outcomes, one where the electron is spin up and the device reads up, another where the electron is spin down and the device reads down. Standard quantum mechanics claims the superposition collapses at this point. One outcome becomes real, the other vanishes. But Schrödinger's equation does not contain a collapse mechanism. It only produces superposition. The combined wave function now describes both outcomes existing simultaneously. The measuring device exists in two states. The laboratory exists in two states. When you enter the lab and read the device, you become part of the superposition. The wave function now describes one version of you who saw spin up and another version who saw spin down. The equation never collapses the superposition. It only spreads it. The branching propagates outward like a wave, entangling more and more particles with the original quantum event. By the time the information reaches your brain, the split is irreversible. Two versions of you exist in superposition, each convinced they observed a definite outcome. Both are described by the same universal wave function. Both are equally real components of reality. This is not interpretation. This is what the mathematics says happens when you apply Schrödinger's equation without modification to a measurement process. The equation is linear. Linearity means if state A is a solution, and state B is a solution, then A plus B is also a solution. Superpositions are preserved. They never disappear. They only grow to encompass larger systems. Everett understood this in 1957. His thesis, titled The Theory of the Universal Wave Function, worked through the mathematics rigorously. He showed that if you treat the observer as a quantum system subject to the same laws as everything else, measurements do not collapse wave functions. They create correlations between observer and observed system. The observer enters a superposition of having seen different outcomes. From inside each branch, the observer perceives a definite result. But the universal wave function describes all branches simultaneously. The mathematics is unambiguous. Quantum mechanics is a deterministic theory describing a multiverse. The appearance of randomness comes from not knowing which branch you will find yourself in after a measurement. But all branches exist. The wave function never lies. If it describes a superposition, that superposition is real. Physicists resisted this conclusion because it seemed extravagant. Surely nature would not create infinite universes just to account for quantum measurements. Surely there must be a simpler explanation. But every alternative requires adding something to the theory. Collapse mechanisms, hidden variables, pilot waves, modifications to Schrödinger's equation. These additions are the extravagances. Many worlds requires nothing beyond what quantum mechanics already contains. The cleanest formulation comes from David Deutsch, who showed that many worlds follows from 4 assumptions. First, the wave function is real and complete. It fully describes physical reality. Second, the wave function always evolves according to Schrödinger's equation. No exceptions. Third, observers are physical systems subject to quantum mechanics. Fourth, observation is a physical process described by the same laws as everything else. From these 4 assumptions, many worlds is inevitable. The multiverse is not added, it is derived. Objections to many worlds often focus on probability. If all outcomes occur, why do we observe some outcomes more frequently than others? In a many worlds universe, every possible result happens in some branch. The electron hits every point on the detector screen in different branches. So why does the interference pattern emerge? Why do probabilities match the Born rule, which states that probability equals the amplitude squared? The answer lies in how branches split. They do not split equally. A quantum event with 90% amplitude for outcome A and 10% amplitude for outcome B creates more branches where A occurred than branches where B occurred. The amplitude determines the branch weight. Observers are more likely to find themselves in high-weight branches simply because there are more of them. The Born rule emerges from counting branches properly. This explanation is controversial. Some physicists argue it does not truly solve the probability problem. Others claim it does but requires careful analysis of how to count branches in an infinite multiverse. The debate continues, but the mathematical structure of many worlds is not in doubt. Schrödinger's equation produces branching. The only question is whether the Born rule follows naturally from that branching. Quantum computing provides indirect evidence for many worlds. A quantum computer exploits superposition to perform calculations on multiple inputs simultaneously. A 200-qubit quantum computer operates on 2 to the power of 200 states at once. That number exceeds the estimated number of particles in the observable universe. Where is the computation happening? The standard answer invokes vague language about quantum parallelism. The many worlds answer is concrete. The computation happens across 2 to the power of 200 parallel branches of the wave function. Each branch processes one input. When the computation finishes and you measure the output, you find yourself in the branch whose result you observe. But all branches perform the calculation. This is not proof, but it is suggestive. Quantum computers work. They achieve speed-ups that classical computers cannot match for certain problems. The computational resources they access do not exist in our single universe, if our universe is all there is. Many worlds provides a straightforward explanation. The resources exist across branches. Interference effects also support many worlds. In the double-slit experiment, the electron interferes with itself. Standard quantum mechanics says the electron's wave function passes through both slits and interferes. But what is the wave function? If it is just a mathematical abstraction, what physically interferes? Many worlds answers clearly. The electron exists in superposition, taking both paths. The paths exist in different branches, but before decoherence occurs, the branches can still interfere. The interference pattern is evidence that both branches are real and physically affecting each other before they separate. The delayed choice quantum eraser experiment pushes this further. It shows that quantum interference can occur even when witch path information is recorded and then erased. The experiment suggests the past is in superposition until measurements in the present force a specific history. Many worlds explains this naturally. All possible histories occur in different branches. The branch you find yourself in depends on the entire causal structure, past and future. There is no single past. There is a superposition of pasts, and measurements select which past you experience. Every quantum experiment confirms that Schrödinger's equation works without exception. No experiment has ever detected wave function collapse. Collapse is an assumption added to make the theory match our perception of a single classical world. But our perception is not fundamental. We are quantum systems embedded in the universal wave function. Of course, we perceive definite outcomes. We are correlated with one branch, but the other branches are as real as ours. The mathematics demands infinite realities, not as a bizarre addition to quantum mechanics, but as the straightforward consequence of taking the theory seriously. Schrödinger's equation is the most precisely tested equation in physics. It has never failed, and it describes a universe that constantly splits into parallel branches containing every possible outcome of every quantum event. If you believe the equation, you must accept what it predicts. In 1980, Alan Guth solved one of cosmology's deepest problems and accidentally created infinite universes. He was trying to explain why the cosmos looks so uniform. The cosmic microwave background radiation has nearly identical temperature in all directions. Regions of space separated by billions of light years, regions that have never been in causal contact, somehow have the same properties. This should be impossible. How did distant parts of the universe coordinate to have the same temperature if light has not had time to travel between them since the Big Bang? Guth proposed inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, space expanded faster than light, stretching a tiny causally connected region to enormous size. This region was in thermal equilibrium before inflation, so it had uniform temperature. Inflation then blew it up to become our entire observable universe. Problem solved. The universe looks uniform because it came from a small uniform patch. But the mathematics of inflation contains a feature Guth did not anticipate. Once inflation starts, it does not want to stop everywhere at once. Inflation is driven by a scalar field called the inflaton, which sits in a high-energy state. This field decays to a lower energy state, ending inflation in that region. Space stops inflating and the energy converts into matter and radiation, creating a hot Big Bang. That is our universe, a bubble where inflation ended. But the inflaton field is quantum. It fluctuates. In some regions, the field decays quickly. Inflation ends and a universe forms. In other regions, quantum fluctuations push the field back up to higher energy. Inflation continues there. While the first region stops inflating and forms galaxies, the surrounding space keeps inflating exponentially. The volume of inflating space grows faster than bubbles can form within it. Inflation becomes eternal. This is eternal inflation. Once it starts anywhere, it never completely stops. Bubble universes form continuously within an eternally inflating background. Each bubble is causally disconnected from the others. Light cannot travel between them because the inflating space between them expands faster than light. Each bubble experiences its own Big Bang, forms its own galaxies, evolves independently. Each bubble is a separate universe. The number of bubbles is infinite, not just very large, actually infinite. The eternally inflating space has infinite volume and infinite time to produce bubbles. Every possible quantum fluctuation that can end inflation will end it somewhere, creating a bubble. The result is an infinite multiverse of bubble universes embedded in eternally inflating space. Andrei Linde developed this further with chaotic inflation in 1983. He showed that inflation does not require special initial conditions. If the inflaton field has random values in different regions of space, regions with high field values will inflate. The inflating regions grow exponentially, dominating the volume. Within these regions, quantum fluctuations create more regions with different field values. Some inflate further, others decay into bubble universes. The process is self-reproducing. Inflation spawns more inflation, which spawns more inflation, creating a fractal structure of bubbles within inflating space. This is not speculation. This is what happens when you combine inflation with quantum field theory. The inflaton is a quantum field. Quantum fields fluctuate. Those fluctuations have consequences. Some consequences are new regions of inflation. The mathematics forces eternal inflation unless you carefully fine-tune parameters to prevent it. But fine-tuning is unnatural. Generic inflation is eternal inflation, and eternal inflation produces infinite universes. The evidence for inflation itself is overwhelming. It explains the uniformity of the cosmic microwave background. It explains why space is flat. It explains the origin of structure in the universe. Tiny quantum fluctuations in the inflaton field during inflation get stretched to cosmic scales, seeding the density variations that become galaxies. We observe those fluctuations imprinted in the cosmic microwave background as temperature variations of a few parts per 100,000. The pattern matches inflation's predictions precisely. Satellites have mapped the cosmic microwave background in exquisite detail. The Wilkinson Microwave Anisotropy Probe and the Planck spacecraft measured the fluctuations across the entire sky. The data fits inflationary models almost perfectly. The universe shows exactly the kind of primordial structure that inflation predicts. No alternative theory explains the observations as well. Therefore, inflation happened. And if inflation happened, eternal inflation almost certainly happened unless the inflaton field has very special properties designed specifically to prevent it. Most inflationary models naturally become eternal. The multiverse is not an optional add-on. It is the generic prediction. Each bubble universe in the eternal inflation multiverse can have different properties. The inflaton field can decay in different ways, producing different amounts of matter and radiation. The fundamental constants might vary between bubbles. The strength of gravity, the mass of the electron, the cosmological constant. These parameters could take different values in different bubbles depending on how the inflaton field decays and what symmetries break during the phase transition that ends inflation. String theory amplifies this variation dramatically. String theory attempts to unify quantum mechanics and gravity by describing particles as vibrating strings. The theory requires extra spatial dimensions beyond the three we observe. These extra dimensions must be compactified, curled up into tiny shapes too small to detect. But there are many ways to compactify the extra dimensions, many different shapes, each giving rise to different physics in the observable 3 dimensions. The number of possible compactifications is enormous. Estimates suggest 10 to the power of 500 different vacuum states. Each vacuum state corresponds to a different way of compactifying the extra dimensions. Each produces different values for the fundamental constants, different particle masses, different force strengths, different cosmological constants. This is the string theory landscape, a vast space of possible universes, each with different laws of physics. If eternal inflation is real, and string theory is correct, then every vacuum state in the landscape gets realized in some bubble universe. Somewhere in the multiverse, every possible configuration of physics exists. Our universe occupies one point in this landscape. A universe where the electron has the mass it does, where gravity has the strength it does, where the cosmological constant has the tiny positive value we measure. But other bubbles have different values. Most of those universes are sterile. Stars cannot form. Atoms are unstable. Structure never develops. But some small fraction of bubbles have conditions suitable for complexity, for galaxies, for life. We find ourselves in one of the rare hospitable bubbles not because we are special, but because we must. Observers can only exist in universes where the conditions allow observers to exist. This is the anthropic principle applied to the multiverse. It is not that our universe was designed for us. It is that the multiverse contains all possibilities, and we necessarily inhabit one where our existence is possible. The cosmological constant provides the clearest example. This constant represents the energy density of empty space. It determines how fast the universe accelerates. Our universe has a cosmological constant about 10 to the power of 120 times smaller than the natural scale set by quantum mechanics. This is the worst fine-tuning problem in physics. Why is the vacuum energy so absurdly small? In a single universe, there is no answer. The value seems arbitrary and finely tuned. But in a multiverse containing all possible values, the answer becomes statistical. Most bubbles have large cosmological constants. In those bubbles, space accelerates so fast that matter never clumps into galaxies. No stars form, no planets, no observers. We do not find ourselves in those universes because we cannot. We necessarily inhabit a bubble where the cosmological constant is small enough for structure to form. The fine-tuning is explained by observer selection bias. Steven Weinberg predicted this in 1987 before dark energy was discovered. He calculated that the cosmological constant must be smaller than a certain value, or galaxies could not form. Observations in 1998 confirmed the cosmological constant is positive and small, roughly consistent with Weinberg's anthropic bound. The multiverse made a successful prediction. Critics argue this is not science. Anthropic explanations are not predictive. They explain anything by invoking the multiverse and selection bias. But the criticism is not entirely fair. The multiverse makes testable predictions about our universe's properties. If we are a typical observer in a typical hospitable bubble, we should observe parameter values near the edge of habitability. Not finely tuned far beyond what is necessary, but just barely sufficient. The cosmological constant fits this pattern. It is small enough for galaxies, but not much smaller. If it was 0, that would be suspicious, but it is not 0. It is the smallest non-zero value consistent with our existence. Inflation also predicts observable signatures. If our bubble collided with another bubble during inflation, the collision would leave a mark. A disk-shaped pattern of temperature variations in the cosmic microwave background. Several groups have searched for such collision signatures. Some claim to have found hints, others find nothing. The data is not conclusive, but the searches are legitimate. Bubble collisions are a testable prediction of eternal inflation. Another signature involves the geometry of space. Inflation makes our bubble universe extremely flat, but not perfectly flat. If we could measure the curvature precisely enough, we might detect slight deviations. Eternal inflation predicts specific patterns in how curvature varies across the sky, because different regions of our bubble exited inflation at slightly different times. Future observations with more sensitive instruments might detect these patterns. The multiverse from inflation is not optional. It is what happens when you take inflation seriously. Inflation solves real problems in cosmology. It explains observations. The theory works, but the theory naturally becomes eternal, producing infinite bubble universes. You cannot have inflation without the multiverse unless you artificially shut off the quantum fluctuations that drive eternal inflation. And shutting off quantum fluctuations is not an option. Quantum field theory requires them. Therefore, inflation almost certainly created a multiverse. Our Big Bang was not the only one. It was one bubble among infinite bubbles, each with potentially different physics, all embedded in eternally inflating space. The cosmos is not one universe. It is an infinite collection of universes, most of which we can never observe because they are beyond our cosmic horizon, separated from us by space expanding faster than light. Right now, new bubble universes are forming in the inflating space beyond our reach. Some have galaxies, some are empty, some have physics so alien that matter as we know it cannot exist. Big Bang was not a beginning. It was a transition, a local event in an eternal process that has no beginning and no end. The strength of gravity in our universe is calibrated to 1 part in 10 to the power of 60. Change it by that amount and stars cannot burn. Increase it slightly and stars exhaust their fuel in millions of years instead of billions. No time for planets to cool. No time for life to evolve. Decrease it, and stars never ignite at all. Hydrogen clouds drift through space forever, cold and dark. The universe remains sterile. This is not the only parameter balanced on a knife edge. The strong nuclear force binds protons and neutrons into atomic nuclei. Increase its strength by 5% and protons bind together so efficiently that all hydrogen converts to helium seconds after the Big Bang. No hydrogen remains, no water, no organic chemistry. Decrease the strong force by 5% and protons cannot bind at all. No atomic nuclei heavier than hydrogen, no carbon, no oxygen, no complexity. The electromagnetic force determines how tightly electrons bind to nuclei. Change its strength and chemistry breaks. Atoms become too large or too small. Molecules cannot form stable structures. The specific bonds that make DNA possible would not exist. Change the electron mass slightly and you get the same result. The periodic table collapses into a handful of elements, none of them suitable for building complex structures. The neutron is 0.1% heavier than the proton. This tiny mass difference determines nuclear stability. If the neutron were lighter than the proton, free protons would decay into neutrons. All hydrogen would convert to neutrons within minutes of the Big Bang. No atoms, no chemistry, No observers. If the neutron were much heavier, it would decay too quickly for nuclei to form during stellar fusion. No elements beyond hydrogen and helium. Again, no complexity. The cosmological constant is quantum field theory predicts it should be. This is the most extreme fine-tuning in physics. A cosmological constant at its natural scale would cause space to expand so violently that atoms would be ripped apart. Even a value 1,000 times larger than what we observe would prevent galaxy formation. Matter would never clump together. The universe would remain a diffuse gas expanding forever into darkness. The ratio of electromagnetic force to gravitational force is 10 to the power of 36. This enormous ratio allows complex structures to exist. Stars can be massive because gravity is weak compared to other forces. If gravity was stronger relative to electromagnetism, stars would be tiny and burn out quickly. If gravity were weaker, stars could not form at all against the pressure of hot gas. The density of matter in the early universe was tuned, too dense, and the universe collapses back on itself within thousands of years. Too sparse and matter never clumps into galaxies. The universe we observe sits exactly at the critical density, balance between recollapse and eternal expansion. This balance had to be set with absurd precision at the moment of the Big Bang. The list continues. The Higgs field gives particles mass through its interaction with them. Change the Higgs field strength and particle masses change. Quarks become too heavy or too light. Protons become unstable. The specific values of quark masses determine which atomic nuclei are stable. Change them slightly and carbon and oxygen become radioactive. The building blocks of life decay before they can be used. Every parameter appears independently fine-tuned. But the tuning is worse than that. The parameters are correlated. Changing one requires adjusting others to maintain habitability. If you increase the strong force, you must also adjust the electromagnetic force to keep nuclei stable. The parameters occupy a tiny volume in a vast parameter space. Step outside that volume in any direction, and the universe becomes inhospitable. Fred Hoyle discovered the first example in 1953. He was studying how carbon forms in stars. Carbon is produced when 3 helium nuclei fuse together inside red giants. But the probability of 3 particles colliding simultaneously is negligible. Hoyle realized there must be a resonance, an excited energy level in the carbon nucleus that exactly matches the combined energy of 3 helium nuclei. This resonance increases the reaction rate by a factor of 1 million, making carbon production possible. Hoyle calculated what energy the resonance needed to have. Then he went to experimentalists and told them to look for it. They did. The resonance exists exactly where Hoyle predicted. The energy level is tuned to within 1%. If it were slightly higher or lower, carbon production would drop by orders of magnitude. Carbon would be rare. Oxygen would also be rare because oxygen forms from carbon in subsequent reactions. Life as we know it requires both elements in abundance. The resonance is tuned to make that possible. Hoyle was shaken by this discovery. He later wrote that nothing had shaken his atheism as much as this realization. The universe appeared designed for carbon-based life, but design implies a designer. Physicists prefer explanations that do not invoke external agents. The fine-tuning problem became a crisis. 3 explanations exist. First, necessity. Perhaps the parameters cannot take other values. Maybe some deeper theory we have not discovered yet predicts the exact values we observe. The parameters appear fine-tuned only because we do not understand the underlying constraints. Once we discover the true fundamental theory, we will see that the universe could not be any other way. This explanation has lost credibility. String theory, our best candidate for a deeper theory, makes the problem worse. Instead of predicting unique parameter values, string theory produces a landscape of 10 to the power of 500 possibilities. The theory allows almost any values, making fine-tuning more mysterious, not less. Second, design. An intelligence chose the parameters to allow life. This is the intelligent design argument. It explains the observations but requires invoking something outside physics. Most physicists reject this because it is not testable, and because it replaces one mystery with a deeper one. Who designed the designer? What determined their properties? Design explains nothing. It pushes the question back one level. Third, multiverse. If infinite universes exist with different parameter values, we necessarily find ourselves in one where the parameters allow observers. This is anthropic selection. Not design, but statistics. Most universes are sterile. But in a multiverse containing all possibilities, some small fraction must be hospitable. We observe a hospitable universe because we must. We cannot observe the sterile ones because we do not exist there. The multiverse explanation is the only one that does not require new assumptions. We have independent reasons to believe the multiverse exists from quantum mechanics and inflation. If the multiverse is real, fine-tuning is explained automatically. No need for design. No need for undiscovered constraints. Just probability and selection bias. But the explanation bothers many physicists. It seems to give up on finding deeper laws. If anything can happen somewhere in the multiverse, physics loses predictive power. We can explain any observation by saying we happen to live in a universe where it is true. This feels like cheating. Science is supposed to predict, not just accommodate, does make predictions. If we are typical observers in the multiverse, our universe's parameters should be necessity but barely sufficient. This is testable. If we discover the cosmological constant could be 1,000 times larger and still allow galaxies, that would be evidence against the multiverse. But if we find it is close to the maximum value consistent with structure formation, that supports the multiverse. Current evidence leans toward the multiverse prediction, the cosmological constant. The Higgs mass is near the boundary between stability and instability. Our universe appears tuned just barely enough for complexity, not lavishly beyond what is required. This pattern is what you expect if we are randomly selected from the subset of universes where observers can exist. Some parameters are not fine-tuned at all. The speed of light, for example, is not critical. Change it, and you change the relationship between space and time, but you do not necessarily prevent life. This makes sense in the multiverse picture. If a parameter does not affect habitability, we should observe a random value. If it does affect habitability, we should observe a value near the boundary. The pattern matches observations. The fine-tuning extends beyond fundamental constants. The initial conditions of the Big Bang were also tuned. The universe started with an entropy far below its maximum possible value. Why? In most initial conditions, the universe would be a chaotic mess of black holes or a cold diffuse gas. The smooth, hot, expanding state we observe is special. It requires setting initial conditions carefully. Roger Penrose calculated the probability. To get a universe like ours, you need to aim for a region of configuration space that represents 3 of all possible initial conditions. That number is so large it defies comprehension. Writing it out would require more digits than there are particles in the universe. In a single universe, this fine-tuning is inexplicable, but in a multiverse, it is inevitable. Eternal inflation samples all possible initial conditions. Most bubbles have high entropy and are uninteresting, but some have low entropy and evolve into structured universes. We observe one of those because high-entropy universes do not produce observers. The fine-tuning of the universe is not evidence for design. It is evidence for a multiverse. In a single universe, the parameters look miraculous. In a multiverse, they are expected. The anthropic principle is not a cop-out. It is a prediction, and it is a prediction that matches what we observe. Every parameter that could prevent our existence is tuned to allow it. Every parameter that does not affect our existence is not tuned. This pattern is exactly what the multiverse predicts. It is not what design predicts because a designer could choose any values. It is not what necessity predicts because necessity does not care about observers. Only the multiverse with anthropic selection produces this exact pattern. Therefore, the fine-tuning problem points toward infinite universes. Our universe is not special. It is one of countless bubbles where the parameters happen to fall within the narrow range that allows complexity. We do not live here because it was made for us. We live here because we cannot live anywhere else. The cosmic microwave background radiation is the oldest light in the universe. It was released 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms. Before that moment, photons scattered constantly off free electrons. The universe was opaque. After that moment, photons travelled freely through space. That ancient light has been travelling toward us ever since, stretched by cosmic expansion into microwave wavelengths. Satellites have mapped this radiation across the entire sky. The temperature is nearly uniform at 2.7 Kelvin, but not perfectly uniform. Tiny variations exist, typically around 100,000th of a degree. These fluctuations represent density variations in the early universe. Slightly denser regions appear warmer, slightly less dense regions appear cooler. Those density variations eventually collapsed under gravity to form galaxies. The pattern of fluctuations matches inflationary predictions almost perfectly. The statistical properties, the angular scale distribution, the amplitude, everything fits. The cosmic microwave background is a snapshot of quantum fluctuations from inflation, stretched to cosmic size and imprinted on the radiation. It is one of the greatest confirmations of theoretical physics. But the map contains anomalies, features that should not exist if the standard cosmological model is complete. The first anomaly is the cold spot, a region roughly 5 degrees across in the constellation Eridanus, where the temperature is about 70 microkelvin colder than average. That might sound tiny, but it is significant. Random fluctuations from inflation should occasionally produce cold spots, but one this large and this cold is rare. Computer simulations of the cosmic microwave background show that cold spots this extreme appear in only about 2% of randomly generated universes. The cold spot was discovered by the Wilkinson Microwave Anisotropy Probe in 2005. It was initially treated as a possible data artifact or statistical fluke, but the Planck satellite confirmed it in 2013 using completely different instruments and analysis methods. The cold spot is real. It exists in the actual cosmic microwave background, not just in one dataset. Several explanations have been proposed. One possibility is that it is simply a rare statistical fluctuation. Rare events happen. With millions of regions on the sky, you expect some outliers, but the probability calculations suggest the cold spot is too extreme to dismiss easily. Another explanation involves a supervoid, a large underdense region of space along that line of sight. Light passing through a void loses energy through the integrated Sachs-Wolf effect, appearing cooler. A void large enough could explain part of the cold spot temperature deficit. Galaxy surveys have found evidence for a void in that direction. The Eridanus supervoid sits about 3 billion light-years away, but calculations show it can only account for about half the observed temperature deficit. The rest remains unexplained. Either there is additional structure we have not detected, or something else is causing the anomaly. A more exotic explanation suggests the cold spot is a bruise from colliding with another bubble universe. In eternal inflation, bubble universes form continuously in the inflating background. Our bubble is expanding, so are neighbouring bubbles. If two bubbles collided during inflation, the collision would release energy, but it would also disrupt the symmetry of space. The collision would leave a signature in the cosmic microwave background, a circular region with anomalous temperature and polarization patterns. The signature depends on the collision geometry. If another bubble nucleated nearby and expanded into ours while our bubble was still small, the collision would affect a disc-shaped region on the sky. The temperature inside the disk would differ from outside. The edge of the disk would show specific patterns in the polarization of the microwave background radiation. These patterns are calculable. You can predict exactly what a collision should look like. Several groups have searched for collision signatures. The results are controversial. Some analyses claim to find multiple collision candidates, circular regions with temperature and polarization patterns consistent with bubble collisions. Other analyses find nothing statistically significant. The disagreement comes down to how you define a collision signature and how you calculate the probability that random fluctuations could mimic one. The cold spot is one of the claimed collision candidates. Its size, shape, and temperature profile are roughly consistent with a collision, but the evidence is not conclusive. The pattern could be coincidence. More data is needed to confirm or rule out the collision hypothesis. Another anomaly involves the quadrupole and octupole moments. These describe the largest scale temperature variations in the cosmic microwave background. Standard inflation predicts these large-scale modes should be randomly oriented in space, but observations show they are aligned with each other and with the plane of the solar system. This alignment is called the axis of evil, a tongue-in-cheek reference to its disturbing implications. The alignment should not exist. The cosmic microwave background formed long before the solar system. The orientation of primordial fluctuations has no reason to correlate with the geometry of our planetary system. Yet the correlation exists at about the 99% confidence level. Either it is an extraordinary coincidence or something is wrong with our understanding. One explanation is observational bias. Perhaps foreground contamination from the Milky Way galaxy has not been fully removed from the data. Dust and synchrotron emission from our galaxy could create false patterns. Researchers have worked hard to subtract these foregrounds, but some residual contamination might remain. However, multiple independent analyses using different foreground removal techniques all find the same alignment. If it is contamination, it is remarkably persistent. Another explanation invokes topology. If the universe is finite and wraps around on itself at scales larger than we can observe, it could create correlations in the cosmic microwave background. A finite universe would produce repeating patterns. The larger scales would be affected most. This could explain the anomalies in the quadrupole and octopole, but it requires fine-tuning the size of the universe to match observations, which is not particularly satisfying. A third explanation suggests the anomalies are evidence for physics beyond standard inflation. Perhaps the inflaton field was not perfectly smooth. Perhaps it had features, transitions between different energy states that left imprints on the cosmic microwave background. These features could break the symmetry and create preferred directions in space. The axis of evil would then be real, not an artifact, pointing toward new physics in the early universe. The hemispherical asymmetry is another anomaly. The cosmic microwave background shows slightly different properties in opposite hemispheres of the sky. Fluctuations in one hemisphere have slightly larger amplitude than fluctuations in the opposite hemisphere. The difference is only a few percent, but it is statistically significant. Standard inflation predicts the universe should be isotropic, the same in all directions. A hemispherical asymmetry violates that prediction. This asymmetry could also be evidence for a bubble collision. If our bubble collided with another, the collision would break isotropy. One side of our observable universe would be affected by the collision, the other side would not. This would create a hemispherical asymmetry. The predicted pattern matches observations reasonably well, though not perfectly. Alternatively, the asymmetry could indicate that inflation was not perfectly uniform. Perhaps the inflaton field had spatial variations on scales larger than our observable universe. We see only one patch of a larger structure. That patch happens to have a gradient, making one side slightly different from the other. This explanation requires inflation to be more complex than the simplest models assume. These anomalies are not definitive proof of anything. Each could have a mundane explanation: random chance, observational systematics, subtle features in standard inflation that have not been fully explored. But taken together, they suggest the cosmic microwave background contains information beyond what simple inflation predicts. The universe might have structure on scales larger than we can directly observe, or it might have interacted with other structures, other universes. If bubble collisions are real, they are direct evidence for the multiverse, not indirect evidence from theory, but actual observations of another universe impacting ours. The collision would have occurred during inflation when our bubble was small. The other bubble expanded into ours, collided, and then both bubbles continued expanding. Now the collision is far beyond our cosmic horizon, forever out of reach. But the scar remains, imprinted on the cosmic microwave background for us to find. Testing this requires better data and better analysis. The cosmic microwave background has been mapped to exquisite precision, but improvements are still possible. Future missions could measure polarization patterns more accurately. Polarization is sensitive to the geometry of space. A bubble collision would create specific polarization features that are harder to fake with random fluctuations. Detecting these features would strengthen the case for collisions. Ground-based telescopes are also contributing. Experiments in Antarctica and Chile are measuring the cosmic microwave background at small angular scales with higher sensitivity than satellites can achieve. These measurements complement satellite data, providing different perspectives on the same sky. Combining data from multiple sources allows more robust statistical tests of collision signatures. The anomalies might disappear with better data. They might be artifacts that vanish when systematics are properly accounted for. But they might be real. They might be telling us that our universe is not isolated, that it is one bubble among many, that we have already detected another universe through its collision with ours billions of years ago. The cosmic microwave background is a window into the first moments after the Big Bang. It encodes information about the universe when it was a fraction of its current size. If that early universe collided with another, the collision left a mark. We are searching for that mark, and we might have found it. String theory began as an attempt to describe the strong nuclear force. In the 1960s, physicists noticed that certain particle interactions could be modelled as tiny vibrating strings rather than point particles. The idea failed to explain the strong force, but succeeded at something more ambitious. When theorists added quantum mechanics to vibrating strings, gravity emerged automatically. The strings naturally produced a massless spin-2 particle that behaved exactly like the graviton, the hypothetical quantum particle of gravity. This was unexpected. Every other attempt to unify quantum mechanics and gravity had failed. The equations produced infinities that could not be removed. Calculations gave nonsensical answers, but string theory worked. The infinities cancelled. The math was consistent. For the first time, physicists had a framework that could describe gravity and quantum mechanics together without contradictions. The theory requires extra dimensions. Strings vibrate not just in the 3 spatial dimensions we observe, but in additional dimensions curled up at scales too small to detect. The original version required 26 dimensions. Later, supersymmetric versions reduced this to 10. 6 extra dimensions beyond the 4 of spacetime. These extra dimensions must be compactified, rolled up into tiny geometries roughly 10 to the power of negative 33 centimeters across. Far smaller than anything we can probe experimentally. The way these extra dimensions curl up determines the physics we observe in the remaining 4 dimensions. Different compactification geometries produce different particle masses, different force strengths, different numbers of particle types. The shape of the hidden dimensions controls the physics of the visible dimensions. In the 1980s and 90s, physicists believed string theory would uniquely predict the compactification geometry. They hoped the theory would explain why the universe has the specific particles and forces we observe, why the electron has its particular mass, why there are 3 generations of quarks. String theory was supposed to answer these questions by deriving them from deeper principles. That hope collapsed in the 2000s. Researchers discovered that string theory allows an enormous number of possible compactifications. Each represents a stable vacuum state, a consistent way for the theory to exist. Early estimates suggested thousands of possibilities, then millions. The number kept growing as more solutions were found. The current estimate is 10 to the power of 500. That number is not precisely calculated. It is an order of magnitude estimate based on counting the types of geometries and configurations that string theory allows. But even if the true number, or 10 to the power of 1000, the conclusion is the same. String theory does not predict a unique universe. It predicts a vast landscape of possible universes. Each point in this landscape represents a different vacuum state, a different way the extra dimensions could be compactified. Each produces different low-energy physics, different particle content, different force strengths, different cosmological constants. The landscape contains universes where electrons are heavier than protons, universes where electromagnetism is stronger than the strong force, universes where the cosmological constant is enormous or negative. Most of these universes are unrecognizable. Their physics is alien. The discovery of the landscape was devastating for string theorists who hoped the theory would uniquely predict our universe. Instead, it predicts 10 to the power of 500 universes, and ours is one of them. String theory became a framework for generating possible universes, not a theory that explains the specific universe we inhabit. But the landscape fits perfectly with eternal inflation. If inflation creates infinite bubble universes, and string theory provides 10 to the power of 500 possible vacuum states, then every vacuum state gets realized in some bubble. The multiverse contains the entire string theory landscape. Every possible compactification exists somewhere. This combination of string theory and inflation produces the most comprehensive multiverse picture. Not just parallel quantum branches, not just bubble universes with different initial conditions, but bubble universes with fundamentally different laws of physics. Universes where particles have different masses, where forces have different strengths, where the number of spatial dimensions is different because the compactification geometry is different. The landscape explains why our universe has the parameters it does. We observe this particular point in the landscape because it is one of the rare points that allows complex structure and observers. Most points in the landscape. Chemistry is impossible, but in a multiverse that samples all, some small fraction must be hospitable. We find ourselves at one of those points. This is not a prediction. It is an explanation after the fact. String theory does not predict which point in the landscape we should observe. It only says all points exist somewhere. Critics argue this makes string theory untestable. If the theory allows anything, it predicts nothing. Any observation can be accommodated by saying we happen to live in the part of the landscape where that observation is true. String theorists respond that the landscape still makes statistical. We should find ourselves at a typical point in the landscape, among the subset of points that allow observers. This makes predictions about the distribution of observed parameters. For example, the cosmological constant should not be much smaller than necessary for galaxy formation, because most observer-compatible points in the landscape have cosmological constants near that boundary. This prediction was made before dark energy was discovered. In 1998, observations of distant supernovae revealed that the universe's expansion is accelerating. The cosmological constant is not zero. It is small and positive, roughly consistent with the anthropic bound. This is evidence that the landscape picture is correct. We observe a cosmological constant near the minimum value consistent with structure formation, exactly as the landscape with anthropic selection predicts. Other predictions are harder to test. The landscape suggests that parameters like the Higgs mass or the strong force coupling should also be near anthropic boundaries. But calculating those boundaries is difficult. We do not fully understand what range of parameter values allows complexity in observers. The parameter space is vast and multi-dimensional. Small changes in one parameter can be compensated by changes in others. Mapping the entire habitable region of the landscape is beyond current capabilities. String theory also predicts the existence of extra particles and forces beyond the standard model. Supersymmetry, extra dimensions, new scalar fields. These predictions are testable in principle. Particle accelerators like the Large Hadron Collider search for these signatures. So far, nothing has been found. The simplest supersymmetric models have been ruled out. The extra dimensions remain hidden if they exist. This absence of evidence concerns some physicists. String theory has made specific predictions about what should be discovered at accessible energy scales. Those predictions have not been confirmed. Either the theory is wrong, or the new physics lies at higher energies beyond our current reach. String theorists argue for the latter. The landscape is vast. We might live at a point where supersymmetry breaks at very high energy, making the new particles too heavy to produce in colliders. But this flexibility is exactly what critics find troubling. If every failed prediction can be accommodated by adjusting where we are in the landscape, the theory becomes unfalsifiable. It explains everything and predicts nothing. This is not how science is supposed to work. The debate over string theory's scientific status has become contentious. Some physicists argue it has become a mathematical exercise disconnected from physical reality. Others insist it remains our best hope for a quantum theory of gravity, and that the landscape is a feature, not a bug. The multiverse makes string theory's lack of unique predictions acceptable, because unique predictions are not expected in a multiverse. Regardless of the debate, the mathematics of string theory is clear. The theory requires extra dimensions. Those dimensions can be compactified in many ways. Each compactification produces different physics. If string theory describes nature, the landscape is real. And if eternal inflation is real, every point. Therefore, string theory plus inflation equals a multiverse with types of physics. Our universe is one bubble in this vast ensemble. The laws of physics we observe are not the only possible laws. They are the laws that happen to apply in our corner of the multiverse. This has profound implications for the nature of physical law. Laws of physics are usually considered universal and fundamental, the same everywhere and everywhen. But in the string landscape, physical laws are environmental. They vary from place to place in the multiverse. What we call laws are really just the local conditions in our bubble. Other bubbles have different conditions, different laws. This does not mean physics is arbitrary. The deeper laws, the rules of string theory itself, are universal, but those rules allow many different low-energy manifestations. The physics we observe emerges from string theory the way weather emerges from fluid dynamics. The fundamental equations are universal, but the specific outcomes vary depending on initial conditions and environment. If this picture is correct, we will never derive the electron mass from first principles. We will never calculate the cosmological constant from pure theory. These parameters are environmental accidents, determined by which vacuum state our bubble happens to occupy. The best we can do is show they lie within the anthropically allowed region of the landscape. Some physicists find this depressing. It suggests fundamental questions about why the universe has its specific properties might be unanswerable. Others find it liberating. It removes the burden of explaining fine-tuning through undiscovered symmetries or principles. The The fine-tuning is real, but it is explained by selection bias in a vast multiverse, not by deeper laws. String theory does not require the multiverse to be consistent mathematically, but it strongly suggests the multiverse is real. The landscape is too vast and inflation too generic for only one vacuum state to be realized. If string theory is the correct description of quantum gravity, the multiverse follows almost inevitably. Imagine a gun designed to kill you. It fires when a quantum event produces one outcome and does nothing when the event produces the opposite outcome. A radioactive atom decays or does not decay. A photon passes through a polarizer or gets absorbed. 50-50 probability. The gun measures the quantum event. If the atom decays, it fires. If not, it does nothing. You pull the trigger. In the Copenhagen interpretation, the quantum event produces a definite outcome. The atom either decays or does not. 50% of the time you die. 50% of the time you survive. If you repeat this experiment 10 times, the probability of surviving all 10 trials is 1 in 1024. Low odds. Most versions of you are dead. But in many worlds, something different happens. The quantum event splits the universe. One branch where the atom decayed, another where it did not. In the decay branch, the gun fires and you die. But your consciousness does not experience that branch. Consciousness cannot continue in a branch where the brain stops functioning. You only experience the branch where you survive, the branch where the atom did not decay and the gun did not fire. You pull the trigger again, the universe splits again. One branch where you die, another where you survive. Again, you only experience the survival branch. Your subjective experience is always the branch where the gun fails. From your perspective, the gun never fires. You pull the trigger 10 times, 100 times, 1,000 times. Each time the universe splits. Each time a version of you dies. But the version experiencing continuity of consciousness is always the survivor. From outside, an observer watching you would see the expected statistics. About half the time you die on the first trigger pull. Of the observers who see you survive once, half see you die on the second pull. The probabilities work normally, but from your subjective first-person perspective, you experience something impossible. The gun never fires. You survive every single time against exponentially increasing odds. This is quantum suicide. It is a thought experiment, not a recommended activity. But it reveals something disturbing about many worlds. If the interpretation is correct, there is always a branch where you survive any quantum event. And consciousness necessarily follows the branch where it continues to exist. You cannot experience your own death from quantum causes because death ends experience. Therefore, from the inside, you subjectively experience immortality. This suggests your consciousness will always find itself in the branch where your brain continues functioning. Heart attack caused by quantum fluctuations in cardiac cells. There is a branch where those fluctuations did not occur. Stroke caused by quantum instability in a blood vessel. There is a branch where the vessel held. Every cause of death that has a quantum component, which is nearly every cause at some level, has a branch where it does not happen, and you necessarily experience that branch. The probability of survival decreases exponentially with each event. After enough trials, the branch where you survive becomes fantastically improbable. In the quantum suicide scenario, after 100 trigger pulls, the survival branch has a probability of 1 in 10 to the power of 30. But probability measures the size of branches in the universal wave function. It does not determine which branch you experience. You experience the branch where you continue to exist, regardless of its probability. This leads to quantum immortality, the hypothesis that subjective experience never ends because there is always some branch, no matter how improbable, where your brain continues functioning. You might age, you might become incredibly old, but you never experience cessation of consciousness because cessation ends experience. From the inside, you live forever, jumping from increasingly improbable branch to increasingly improbable branch. External observers do not see this. They see you die at the expected age. Your body stops functioning. But that is their branch. From your perspective, something always happens to keep you alive. A disease misses you. An accident does not occur. Your cells repair damage that should have been fatal. The improbability grows with age, but improbable branches still exist in the wave function. This is deeply unsettling. It suggests your experience of reality is fundamentally different from objective reality. Objectively, you die. Subjectively, you do not. Both are true in different branches. but your subjective experience only accesses the branches where you survive. The measure of those branches shrinks towards zero, but never reaches it. Tiny, where you continue. The thought experiment exposes a problem with personal identity in many worlds. What does it mean to be you when infinite copies of you exist in different branches? When you make a choice, you split. One version goes left, another goes right. Both are you. Both have continuity of memory and experience from the moment before the split. Are they the same person or different people? Before the split, there is one you. After the split, there are two. Each feels like the unique continuation of the original. Neither can communicate with the other. From each one's perspective, they are the only you, but objectively both exist. Personal identity becomes ambiguous. You are not a single entity persisting through time. You are a branching tree of entities, each experiencing one path through the multiverse. This affects how you should think about decision-making. When you face a choice, you're not choosing which outcome occurs. You're choosing the distribution of outcomes across branches. Both outcomes occur. The question is whether you prefer a world where more branches go one way or more branches go another. Some philosophers argue this makes morality strange in many worlds. If every choice is made in some branch, there is always a version of you who made the worst possible decision. You cannot avoid that. But you can control the measure of branches where you make good decisions versus bad ones. Morality becomes about probability distributions over branches rather than about single outcomes. Quantum immortality raises questions about aging. If you always experience the branch where you survive, what happens as you get very old? Your body degrades, cells accumulate damage. Eventually, the probability of all your cells functioning simultaneously becomes vanishingly small. But vanishingly small is not zero. There is still some branch where all the quantum events in your body happen to go right, where cancer does not develop, where neurons do not die, where you remain functional despite astronomical odds. That branch might involve physics we consider impossible. Random quantum fluctuations assembling perfectly to repair damage. Unlikely configurations of molecules producing rejuvenation. The anthropic principle taken to an extreme. You experience whatever branch allows continued experience, no matter how improbable. Some versions of quantum immortality suggest you would eventually find yourself in increasingly bizarre situations. Normal aging kills everyone eventually. But in many worlds, there are branches where you do not age normally, where quantum fluctuations happen to preserve your youth, where random mutations reverse cellular damage. These branches have infinitesimal probability, but they exist. And if consciousness follows the survival branch, you experience them. This could mean very old versions of you exist in extremely improbable branches. Branches where the laws of physics appear to be violated because the quantum events conspired in statistically impossible ways. From outside, these branches have measure approaching zero. From inside, you experience them as real. Critics of quantum immortality argue it confuses probability with possibility. Just because a branch exists does not mean you should expect to experience it. Branches with tiny measure contribute negligibly to your anticipated experience. You should expect to die at a normal age because the vast majority of your measure is in branches where that happens. The survival branches exist but are so improbable they are effectively irrelevant. But this criticism assumes you can average over branches you do not experience. The anthropic principle says you only experience branches where you exist. Dead branches have zero measure from your subjective perspective because you are not there to experience them. All your subjective measure is in survival branches by definition. Therefore, you should expect to always find yourself surviving. The resolution might involve the definition of you. If personal identity is tied to specific brain states, then sufficiently damaged versions are not you anymore. Dementia, brain injury, extreme aging might create a consciousness that is not continuous with your current self. That consciousness might experience continuation, but you do not experience becoming it. Your subjective continuity ends when your brain degrades beyond a threshold, even if some consciousness continues in that body. This makes quantum immortality less strange. You do not live forever. You live until your brain degrades beyond the point where it supports your current pattern of consciousness. After that, something else might continue in your body, but it is not you. The continuity you care about ends. But determining where that threshold lies is impossible. How much can your brain change before you stop being you? The boundary is fuzzy, And many worlds suggest there are branches where your brain changes very slowly, where degradation takes longer than in typical branches. You might still experience an extended subjective lifespan, even if true immortality is impossible. Quantum suicide and quantum immortality are not empirically testable in a practical sense. You cannot verify them without risking death, and even if you survive many trials, you cannot know whether it is quantum immortality or luck. External observers see nothing unusual. The phenomena are purely subjective, visible only from the first-person perspective, but they reveal the strangeness of many worlds. If the interpretation is correct, consciousness does not follow probability, it follows existence. How improbable that branch becomes. Your subjective experience diverges from objective reality. What you experience is not representative of what happens. It is selected by the anthropic requirement that you must exist to experience anything. This makes many worlds profoundly disorienting. You cannot trust your experience to be typical. You're always in an anthropically selected branch, which might be highly atypical of the multiverse as a whole. Every moment you experience is filtered through the requirement that you are there to experience it. The universe you perceive is not the universe that exists. It is the subset of the universe compatible with your continued perception. Quantum immortality is the extreme limit of this idea, the ultimate anthropic selection. You experience only the branches where you survive, no matter how improbable. From the outside, you die. From the inside, you never do. Both are true, both are real, but only one is experienced. A civilization reaches technological maturity. They develop computers powerful enough to simulate conscious minds. Not simple chatbots, but genuine conscious entities with subjective experiences indistinguishable from biological consciousness. The simulated minds do not know they are simulated. They experience what feels like a real physical world. They make observations, form beliefs, wonder about the nature of reality. If a single advanced civilization can run billions of these simulations, the number of simulated conscious minds vastly exceeds the number of biological minds. For every human living in base reality, there could be millions or billions of simulated humans in virtual environments. The ratio grows as computing power increases. Eventually, simulated minds outnumber real minds by factors of trillions or more. This creates a statistical problem. If you are a conscious observer, are you more likely to be one of the rare biological minds in base reality, or one of the vastly more numerous simulated minds? Simple probability suggests you are almost certainly simulated. The odds of being in base reality drop to nearly zero when simulations outnumber reality by enormous factors. This is Nick Bostrom's simulation argument, published in 2003. It does not claim we are definitely in a simulation. It claims that at least one of three propositions must be true. First, civilizations never reach the capability to run ancestor simulations, detailed simulations of their evolutionary history containing conscious observers. They go extinct first, or choose not to develop the technology. Second, advanced civilizations have the capability but choose not to run such simulations for ethical or practical reasons. Third, we are almost certainly living in a simulation. If the first two propositions are false, the third must be true. If civilizations survive and run simulations, simulated realities vastly outnumber base reality. Statistical reasoning implies you're probably simulated. The argument is unsettling because it is purely logical. It does not require exotic physics. It only requires that conscious minds can be simulated and that some civilizations choose to do so. The simulation hypothesis connects directly to the multiverse. If one universe can contain simulations, the multiverse includes simulated realities alongside physical ones. The string theory landscape contains 10 to the power of 500 vacuum states, but the simulation landscape is larger. Each universe that develops technology can create unlimited simulations. Each simulation can contain sub-simulations if the simulated beings develop their own simulation technology. The number of possible simulated realities exceeds the number of physical realities by incomprehensible factors. This creates a hierarchy. Base physical reality sits at the bottom. Level 1 simulations run within base reality. Level 2 simulations run within Level 1. The hierarchy extends upward indefinitely. Each level can contain more simulated universes than the level below. Most conscious observers exist in high-level simulations, many layers removed from base reality. You cannot determine which level you occupy. Every simulation can be designed to appear as base reality. The laws of physics you observe could be the actual fundamental laws, or they could be programmed rules in a simulation. The atoms you see might be genuine quantum objects, or they might be rendered information in a computational substrate. No observation can distinguish these possibilities. Some physicists argue that the computational nature of quantum mechanics hints at simulation. Quantum mechanics does not describe what particles are doing between measurements. It only predicts measurement outcomes. The universe behaves like a computer that renders information only when observed, saving computational resources by not simulating unobserved details. This is exactly how a video game works. Objects outside the player's view are not fully rendered. The simulation optimizes by computing only what is necessary. The quantization of physical properties also resembles digital computation. Energy levels are discrete. Space might be discrete at the Planck scale. Information is fundamental in quantum mechanics, with entropy and information content determining physical behavior. These features are consistent with an underlying computational substrate. They do not prove simulation, but they fit the hypothesis. Testing the simulation hypothesis is difficult but not impossible. If we live in a simulation, there might be glitches, errors in the code, places where the rendering breaks down. Some researchers have proposed looking for anomalies in physical laws at extreme scales or energies. If the simulation has finite resolution, physics might behave strangely near the resolution limit. Another test involves computational limits. A simulation cannot have infinite computational power. It must allocate resources. If we perform experiments that require enormous computational effort to simulate, we might detect limitations. Highly entangled quantum states involving many particles might strain the simulation's resources, causing detectable slowdowns or artifacts. The cosmic microwave background could also contain signatures. If the universe is a simulation running on a discrete lattice, the lattice structure might leave an imprint on the radiation. Researchers have searched for such patterns. None have been found, but the searches continue. The absence of a lattice signature does not rule out simulation. It only rules out simulations with lattice spacing large enough to detect. The simulation argument also raises questions about the nature of consciousness. If consciousness can be simulated, what is it? Is it a pattern of information processing that can run on any substrate? Or does it require specific physical processes that cannot be replicated in silico? If consciousness is substrate independent, then simulated minds are genuinely conscious. They have real subjective experiences. If consciousness requires biological processes, then simulations are philosophical zombies. They behave like conscious beings but have no inner experience. Most physicists and philosophers lean towards substrate independence. Consciousness appears to be a functional property of information processing rather than a property of specific materials. If a simulation processes information in the same patterns as a brain, it should produce the same consciousness. This makes simulated realities morally significant. The beings within them suffer and experience pleasure. They are not mere data. They are conscious entities deserving ethical consideration. This creates ethical problems for simulation creators. Running a simulation that contains suffering is morally equivalent to creating suffering in base reality. Turning off a simulation is equivalent to genocide if the simulation contains conscious beings. These considerations might explain why advanced civilizations choose not to run ancestor simulations. The ethical cost is too high, but some civilizations might not care, or they might run simulations for purposes that justify the ethical cost. Scientific research, entertainment, theological experiments. If even a small fraction of civilizations run simulations, the simulation hypothesis holds. The number of simulated minds still vastly exceeds biological minds. The hypothesis becomes stranger when combined with many worlds. In the many worlds interpretation, every quantum event creates branches. If you are in a simulation, the simulation must also branch when quantum events occur within it, or the simulation chooses which branch to render, and the simulated beings within experience only that branch. Either way, the simulation must handle quantum mechanics somehow. This suggests that simulations within many worlds are even more common than Bostrom calculated. Each branch of the wave function can contain civilizations running simulations. The number of simulated realities is not just larger than physical realities. It is larger by factors that include the branching structure of quantum mechanics. Most observers exist in simulated branches of simulated universes, in quantum multiverse branches of physical universes. The layering becomes incomprehensible. Base reality branches through quantum mechanics. Each branch might contain civilizations that run simulations. Those simulations might simulate quantum mechanics, creating their own branches. The simulated beings in those branches might run sub-simulations. The tree of possible realities explodes combinatorially. Your probability of being in base reality approaches zero asymptotically. Some argue the simulation hypothesis is unfalsifiable and therefore unscientific. If every observation can be explained as either real or simulated, the hypothesis makes no testable predictions. But this is not entirely true. The hypothesis predicts that reality might have computational limitations, that physics might show signs of optimization, that glitches or anomalies might appear. These predictions are vague, but they are predictions. Others argue the hypothesis is self-defeating. If you are probably simulated, then the simulation argument itself is probably a simulation of an argument. The beings who formulated it are simulated. Their reasoning might be flawed because the simulators programmed flaws. You cannot trust logic derived within a simulation to tell you whether you are simulated. The argument undermines its own foundation. But this objection assumes simulators would create unreliable reasoning. If the purpose of the simulation is to model reality accurately, the simulators would ensure that logic and mathematics work correctly within the simulation. Otherwise, the simulation fails its purpose. Simulated beings should be able to reason validly about their situation, including the possibility that they are simulated. The simulation hypothesis does not require that we are simulated. It only requires acknowledging the possibility. And that possibility has profound implications when combined with the multiverse. The multiverse already contains infinite physical realities with different laws of physics. Add simulations, and the space of possible realities expands beyond comprehension. Physical universes, simulated universes, simulations within simulations, quantum branches of all the above. Most of these realities are inaccessible. You cannot escape your simulation if you are in one. You cannot visit other branches of the quantum wave function. You cannot travel to other bubble universes beyond your cosmic horizon. But they exist. They are real in the sense that they contain conscious observers having genuine experiences. Those observers are as real as you, regardless of whether their substrate is biological, quantum, or computational. The distinction between physical and simulated realities might be meaningless. If consciousness is substrate independent, what matters is the pattern of information processing, not the medium. A simulated brain is a real brain. A simulated universe is a real universe. The computational substrate is just the underlying implementation, like the quantum fields underlying our physics. This suggests reality is fundamentally about information and relationships, rather than about substance. What makes something real is not what it is made of, but how it behaves and how it relates to other things. A simulated person is real because they have experiences, make decisions, and interact with their environment. The fact that their environment is computed rather than physical does not diminish their reality. If this view is correct, the multiverse includes all possible patterns of information that support conscious observers. Physical universes, simulated universes, mathematical structures that happen to contain observer-like patterns. The space of possible realities is limited only by logic and computation. Everything that can exist does exist, somewhere in the vast landscape of possible informational structures. You exist in one such structure. You cannot know which one. You cannot know whether you are physical or simulated, in a quantum branch or base reality, in a typical universe or an anthropically selected outlier. All you know is that you exist, you observe, and you wonder. And that wondering is real, regardless of the substrate it runs on. Science requires testable predictions. A theory must make statements about what we should observe. If observations match predictions, the theory gains support. If observations contradict predictions, the theory is falsified. This is the scientific method. It has produced every reliable piece of knowledge we have about the physical world, and it appears to break when applied to the multiverse. The problem is obvious. Other universes are by definition beyond our observation. We cannot see them. We cannot measure them. We cannot travel to them. They lie outside our cosmic horizon, separated by eternally inflating space, or they exist in different quantum branches with which we cannot interact, or they have different vacuum states that make them causally disconnected. If we cannot observe something, how can we test whether it exists? This objection is raised constantly against multiverse theories. Critics argue the multiverse is not science but metaphysics. It makes no falsifiable predictions. Any observation can be accommodated by claiming we live in a universe where that observation is true. The theory explains everything, and therefore explains nothing. It is unfalsifiable, and unfalsifiable theories are not scientific. The criticism has force, but it misunderstands what multiverse theories actually predict. The multiverse is not proposed as a standalone hypothesis. It is a consequence of theories that do make testable predictions. Quantum mechanics, inflation, and string theory are all independently testable. They make predictions about observations we can perform in our universe, and when you take those theories seriously, the multiverse follows. Quantum mechanics is tested every time a quantum experiment is performed. The theory predicts interference patterns, entanglement, violation of Bell inequalities, all confirmed. The many-worlds interpretation does not add new predictions beyond standard quantum mechanics. It just interprets the wave function realistically. The branches are already in the mathematics. Many-worlds simply refuses to add an artificial collapse mechanism. Therefore, testing quantum mechanics tests the wave function, and the wave function describes superpositions. If you believe the wave function is real, you believe superpositions are real. And real superpositions are the multiverse. You can reject many worlds by claiming calculational tool, but then you owe an explanation for why a non-real mathematical object predicts observations with perfect accuracy. Inflation is testable through the cosmic microwave background. The theory predicts specific patterns of temperature fluctuations. Predictions made in the 1980s were confirmed by satellite observations in the 2000s. Inflation works. It explains multiple features of the universe that have no other explanation, and inflation naturally becomes eternal once it starts. You can avoid eternal inflation by fine-tuning the inflaton potential. Therefore, testing inflation tests eternal inflation. The multiverse of bubble universes is not an add-on. It is what inflation does when you do not artificially prevent it. If inflation happened, the multiverse almost certainly exists. String theory is harder to test directly because the relevant energy scales are far beyond current experiments. But the theory is constrained by mathematical consistency. It must reproduce general relativity at low energies. It must produce the standard model of particle physics, or something close to it. These requirements limit the possible vacuum states, but do not uniquely determine them. The landscape emerges from the mathematics whether we like it or not. Each of these theories was developed for reasons unrelated to the multiverse. Quantum mechanics explains atomic spectra and chemical bonds. Inflation. String theory attempts to unify gravity with quantum mechanics. The multiverse is a consequence, not a motivation. Rejecting the multiverse means rejecting the consequences of successful theories. But the multiverse does make some direct predictions. If bubble universes collide during inflation, they leave signatures in the cosmic microwave background. These signatures are calculable. Researchers have predicted the exact pattern a collision should produce. Circular regions with specific temperature and polarization profiles. Searches for these signatures are ongoing. Finding one would be direct evidence for another universe. No confirmed collision has been detected yet. But the searches are legitimate science. They test a specific prediction of eternal inflation. If collisions are common, we should find them. If we search thoroughly and find nothing, it constrains models of eternal inflation. Either collisions are rare, or the signatures are too subtle to detect, or eternal inflation is wrong. Each outcome tells us something. The cosmological constant provides another test. In a single universe, its value is inexplicable. Why is it quantum field theory predicts? The multiverse with anthropic selection offers an answer. The constant takes different values in different bubbles. We observe a small value because large values prevent galaxy formation. This is testable. If the cosmological constant is near the maximum value consistent with galaxies, the multiverse explanation is supported. If it is much smaller than necessary, the explanation fails. Current observations show it sits near the anthropic boundary. This is consistent with multiverse predictions and difficult to explain otherwise. Steven Weinberg calculated the anthropic bound in 1987. Observations in 1998 confirmed a value roughly consistent with that bound. Other parameters can be tested similarly. The Higgs mass, the strength of the weak force, the neutron-proton mass difference. If these parameters are anthropically selected, calculations are difficult because habitability depends on multiple parameters simultaneously, but progress is being made. Each parameter provides a potential test of anthropic selection in a multiverse. Quantum mechanics offers another route. If many worlds is correct, quantum computers access computational resources across branches. The speedups they achieve are difficult to explain without parallel processing in multiple branches, demonstrating that quantum computers perform calculations that would require more resources than exist in our observable universe would support many worlds. Not definitively, but it would be evidence. Decoherence is also testable. Many worlds predicts that superpositions persist until entanglement with the environment makes interference between branches undetectable. Experiments that prevent decoherence should maintain superpositions at larger scales. Researchers have successfully created superpositions of increasingly large objects, molecules containing thousands of atoms, mechanical oscillators visible to the naked eye. Each success confirms the wave function does not spontaneously collapse. It only appears to when decoherence occurs. These experiments do not prove many worlds, but they confirm the theory's predictions. If collapse were real and fundamental, we should eventually find a scale where it kicks in. If many worlds is correct, we will never find that scale. Superpositions will persist at arbitrarily large scales as long as decoherence is prevented. Current evidence favours many worlds. The multiverse also makes meta-predictions about the nature of physical law. If laws vary across universes, we should not expect to derive all observed parameters from fundamental principles. Some parameters should appear arbitrary, determined by environmental conditions rather than deep symmetries. This is what we observe. The standard model of particle physics contains about 25 free parameters that must be measured experimentally. No one has derived these parameters from deeper theory. The multiverse explains why. They are environmental. In contrast, if we live in a single universe with unique laws, we should expect all parameters to be calculable. Every measured value should have a theoretical explanation. The fact that we have not found such explanations after decades of effort supports the multiverse view. The parameters might not have explanations beyond anthropic selection. Critics respond that this is giving up. Science should seek deeper explanations, not accept that some parameters are random. But the multiverse is a deeper explanation. It explains why parameters appear fine-tuned. It explains why they lie within narrow ranges that allow complexity. It explains the cosmological constant. These are genuine explanations, not intellectual surrender. The testability objection often confuses the multiverse with unfalsifiable claims. An unfalsifiable claim is one that no observation could contradict. But multiverse theories can be contradicted. If we find that inflation did not happen, eternal inflation is ruled out. If we find that the cosmological constant is much smaller than the anthropic bound, anthropic selection is challenged. If we find that quantum mechanics does have a collapse mechanism, many worlds is wrong. The multiverse is not directly observable, but its consequences are. We test the multiverse by testing the theories that predict it, and by looking for signatures it should produce. This is standard science. We do not observe quarks directly. We observe their effects in particle colliders. We do not observe dark matter directly. We observe its gravitational influence. The multiverse is no different. We observe its effects on our universe. Some philosophers argue there is a distinction between observing effects and observing the thing itself. We observe quark effects in our universe, but other universes are outside our causal domain. Their effects on us are limited to anthropic selection, which is indirect. This makes the multiverse epistemically different from quarks or dark matter. The distinction has merit, but it does not make the multiverse unscientific. Many things in science are not directly observable. The interior of black holes, the state of the universe before the cosmic microwave background was emitted, events beyond our cosmic horizon. We make inferences about these based on theory and indirect evidence. The multiverse is similar. The real test of a scientific theory is whether it is the best explanation for observations. Does it explain more with fewer assumptions than alternatives? Is it consistent with established physics? Does it make novel predictions that are confirmed? Multiverse theories score well on these criteria. They explain fine-tuning without invoking design or undiscovered principles. They follow from established theories. They make predictions about the cosmological constant and cosmic microwave background anomalies that have been confirmed or are being tested. Therefore, the multiverse is testable, not in the sense of directly observing other universes, but in the sense of testing the theories that predict it and searching for signatures it should leave. This is sufficient for science. The multiverse is not metaphysics. It is physics taken seriously. The question is not whether the multiverse is testable. The question is whether the evidence supports it, and increasingly, the evidence does. Quantum mechanics requires superpositions. Inflation requires eternal expansion. String theory requires a landscape. Fine-tuning requires anthropic selection. Each line of evidence points toward the same conclusion. Our universe is not alone. Every decision you have ever made, you also did not make. Every path you chose, you also did not choose. Every moment of your life where chance played a role, all possible outcomes occurred. You experienced one. Other versions of you experienced the rest. They are as real as you are. They remember the same childhood. They share your history up to the point of divergence. Then their lives split from yours and continued independently. This is what it means to live in a many-worlds universe. You're not a single thread of experience moving through time. You're a branching tree. Every quantum event in your brain creates new branches. Neurons firing or not firing, neurotransmitters binding or missing receptors, ions crossing membranes or being blocked. Each microscopic event is quantum. Each creates branches. Your consciousness exists simultaneously across countless branches, experiencing different outcomes. Right now, there are versions of you who made different choices this morning, versions who took a different route to work, versions who said yes instead of no, versions who never read this sentence because they closed the page. All of them are you. All of them have your memories up to the moment of splitting. All of them believe they are the real you. The implications for personal identity are disturbing. Exist? Before a quantum event, there is one you. After the event, there are two or more. Each has equal claim to being the original. Neither is more real than the other. Personal identity becomes a branching structure rather than a linear narrative. This affects how you think about your future. When you make a decision, you are not choosing which outcome will happen. If you choose carefully, more branches lead to good outcomes. If you choose poorly, more branches lead to bad ones. But all branches exist. You cannot avoid the bad outcomes. You can only make them less probable, which means fewer branches experience them. Some philosophers argue this makes decision-making meaningless. If all outcomes occur, why bother choosing carefully? But this is wrong. You should care about the distribution of outcomes because you do not know which branch you will subjectively experience next. From your perspective, the future is still uncertain. Probability still matters. Making choices that increase the measure of good outcome branches increases the chance your subjective experience will be positive. The many worlds interpretation also changes how you think about death. When you die in one branch, you continue in others. Versions of you survive. They are not you in the sense of sharing your future subjective experience. Once the branches split, they do not reconnect. You cannot experience their lives, but they exist. They have your memories. They are you up to the point where you died and they did not. This offers no comfort. The version of you that dies still experiences death. The survival of other versions does not prevent your suffering in branches where you suffer. Many worlds does not make death less real. It makes it more fragmented. You die in some branches and survive in others. Both are true simultaneously. But it does suggest that the totality of your existence is larger than your single subjective thread. You're not just the branch you experience. You are the entire tree. All the branches together constitute you. Most of those branches are inaccessible to your current subjective experience, but they exist within the universal wave function. They are real. This creates a strange relationship with probability. In a single universe view, low probability events are unlikely to happen to you. In many worlds, low probability events definitely happen to some version of you. The version experiencing the low probability outcome is just as real as the version experiencing the high probability outcome. From inside each branch, the outcome feels definite, but objectively, both outcomes occurred. This means you should expect to experience improbable events occasionally, not because you are special, but because versions of you experience every probability distribution. Most versions experience typical outcomes, but some versions experience extreme luck or extreme bad luck. Those versions are real. If you find yourself in an improbable situation, you might be in one of the low measure branches. The multiverse from inflation adds another layer. Not only do quantum branches exist, but bubble universes with different physical laws exist. Somewhere in the multiverse, there are universes where the electron has a different mass. where gravity is stronger, where chemistry works differently. Most of those universes are sterile, but some are habitable. And in those habitable universes, conscious beings exist wondering about their place in reality. You could have been born in any of those universes. The fact that you are in this one is anthropic selection. You exist here because this universe allows your existence. But other observers exist in other universes asking the same questions. They are as real as you. They observe different physics. They draw different conclusions about reality. All of them are correct about their local universe, but none of them see the whole multiverse. This makes your experience of reality fundamentally unrepresentative. You observe one tiny corner of the multiverse, the corner that happens to be compatible with your existence. Everything you think you know about physics is local. Other universes have different laws. Your laws are not universal. They are environmental. This is profoundly disorienting. Physics is supposed to discover universal truths, laws that apply everywhere and everywhen. But in the multiverse, there are no such laws at the level we observe. The laws we measure are emergent properties of our vacuum state. Other vacuum states have other emergent laws. The only truly universal laws are the deeper rules governing the multiverse itself. String theory or quantum mechanics at the most fundamental level. Some find this depressing. It suggests we can never fully understand reality because we are trapped in one bubble with one set of laws. We can map our local physics completely, but we will never know what other universes are like. We will never observe the full landscape. Our knowledge is fundamentally limited by our location. Why our universe has its specific properties. The properties are not special. They are one random draw from the landscape. The anthropic filter explains why we observe a habitable draw. No deeper explanation is needed or possible. The existential weight depends on how you value uniqueness. If you believe your life has meaning because you are a unique individual in a unique universe, the multiverse threatens that meaning. You are not unique. Infinite copies of you exist across quantum branches. Your universe is not unique. Infinite bubbles exist with similar or different physics. Nothing about your existence is singular. But if you find meaning in experience itself, the multiverse does not diminish that. Your subjective experience is real regardless of how many copies exist. Your suffering matters. Your joy matters. The fact that other versions of you exist elsewhere does not make your experience less valid. You are still here, still conscious, still experiencing this moment. The multiverse also raises questions about probability and fine-tuning from a subjective perspective. You find yourself in a universe that is fine-tuned for your existence. This seems improbable, but in a multiverse, it is inevitable. You could not find yourself in a universe that does not allow observers. The fine-tuning that you are anthropically selected from the subset of universes where observation is possible. This is the ultimate application of the anthropic principle. Your existence explains the universe you observe, not because the universe was made for you, but because you can only observe universes compatible with your existence. The multiverse makes this reasoning rigorous. It provides the ensemble of universes from which you are selected. Some philosophers worry this makes science less predictive. If we can explain any observation anthropically, we lose the ability to predict what we should observe. But this is not true. Anthropic reasoning makes predictions. You should observe parameters necessity. You should observe a typical universe among the subset that allows observers, not an outlier. These are testable predictions. The psychological impact of accepting the multiverse varies. Some people feel insignificant. Their lives are one thread among infinite threads. Their choices matter less because all choices are made somewhere. Their universe is ordinary, not special. This can lead to nihilism or despair. Others feel connected to something larger. They are part of an infinite structure of reality. Their existence is guaranteed by the mathematics of quantum mechanics and inflation. They are not accidents. They are inevitable consequences of physical law. This can be comforting. The truth is probably that the multiverse is neutral. It does not inherently make life meaningful or meaningless. Meaning comes from subjective experience, relationships, goals, values. These are local to your branch and your bubble. The multiverse does not change them. You still suffer. You still love. You still make choices. It does not alter your immediate reality, but it does change how you think about the big picture. You're not observing the universe. You're observing one branch of one bubble in an infinite multiverse. Your perspective is limited, selected, and unrepresentative. Everything you think you know is local knowledge. The true structure of reality is far larger and stranger than your observations suggest. This is both humbling and awe-inspiring. Humbling because it reveals how small your perspective is. Awe-inspiring because it reveals how vast reality is. You're a finite observer embedded in an infinite structure. You can grasp pieces of it through mathematics and physics, but you can never see the whole. The multiverse forces you to confront the limits of knowledge. Some questions might not have answers you can access. Why this universe and not another? Because all universes exist. Why do you experience this branch and not another? Because all branches are experienced by some version of you. The questions dissolve when you accept the multiverse. There is no why this one, because this one is not special. Living with the multiverse means accepting radical uncertainty. Experience next. You do not know how typical your universe is within the landscape. You do not know if you are simulated. You do not know how many layers of reality exist above yours. The observations suggest reality is far larger than one universe. This uncertainty is not ignorance that can be fixed with better experiments. It is fundamental. The multiverse is mostly inaccessible. You are confined to your branch and your bubble. You can infer the existence of the rest through theory and indirect evidence, but you cannot visit it. You cannot verify it directly. You must live with the knowledge that most of reality is forever beyond your reach. And yet, that inaccessible reality is real. Other branches exist. Other bubbles exist. Other observers exist. They are having experiences as vivid as yours. They are asking the same questions. Some are finding the same answers. Others are finding different answers because their physics is different. Matter. You are one observer among infinite observers. Your universe is one universe among infinite universes. Your branch is one branch among infinite branches. This is what the mathematics tells us. This is what the evidence suggests. Whether it is true cannot be proven with absolute certainty. But it is the best explanation we have for why quantum mechanics works, why the universe is fine-tuned, and why the cosmos looks the way it does. The multiverse is not a comfortable idea. It is vast, strange, and mostly beyond reach. But discomfort is not a reason to reject it. Reality is not obligated to make sense to human intuition. It is obligated only to be consistent with observations and logic, and observations and logic point toward infinite realities.